In this lecture, we review some applications of quality control charts. A process is the transformation of input into output, and the output is affected by a number of causes and their interactions, which produces variability in the output. This is the revenue from a monthly revenue from a company, and we have collected data for the past several months and establish our central line upper and lower control limits. As you can see, based on the previous data, based on the previous several months, the monthly revenue averages about $12.9 million. The lower control limit is about 10.6, and the upper control limit is about $12.2 million. This is the range of variability in this process, known as process capability, or the voice of the process. This is a predictable process, meaning you can predict the behavior of this process into the near future. One may say, well, this is too much noise, too much variation for decision making. Remember that we calculated these limits using the process data, so what you see is what the process is communicating. If we're not happy with this, then we have to fundamentally change the system and the process. Sometimes a demand is made that is beyond the capability of the current process, perhaps the monthly revenue of $20 million. This is beyond the capability of the current process. How can we achieve that? Well, there are three ways you can achieve that value. Either by distorting the data, or by distorting the system, trying to reach that number no matter at what cost, or improve the system. If we're demanding a value that is beyond the capability, we need to improve this system to a higher level where that value is a part of the system now. So either distort the data, distort the system, and improve the system. This is the same chart. Then again, you see that the process is in a statistical control and predictable. This is another example of a monthly revenue, an individual and moving range chart. Here we show how to calculate the upper and lower control limits, and for the upper chart and the lower chart. Then again, this process is in a statistical control and it's predictable. The monthly revenue averages about 90, and it varies somewhere between 70 to $111 million. You can say that this process is predictable, and that prediction can be used as the basis of forecasting. Here is an example from a chemical process. A sample from 25 batches of a particular chemical has been selected and tested, and these are the pH values. As you can see, this process is also in a statistical control, and you may say that based on the last 25 batches, the pH average is about 6.5, and the range of variation in pH values are between 5.5 to 7.5. Then again, one might decide if this is acceptable or unacceptable and what changes to make. However, any improvement to this system comes from changing the cause system, improving the system that produces this range of variability. Here is an example from healthcare. This is the fasting blood sugar. For the past 30 days, the fasting blood sugar values have been collected. And as you can see, this chart again is in a statistical control. You say that the fasting blood sugar based on the last 30 days averages about 130 and can possibly vary between 83 to 178. Again, if this is not acceptable, any improvement to this, whether we have to lower the average and narrow the variation, or just narrow the variation, any improvement strategy that you have to undertake here comes from improvement of the system as a whole. An extension of using control chart for forecasting, we have already observed this for revenue data, and stated that we can use the upper and lower control limit, the boundaries of the variation, as the boundaries of prediction into the near future. However, we may be able to produce a most likely forecast. Since approximately about 85% of all the observations from a predictable process, a process that is in a statistical control, fall within this middle 50% of the limits in this area, we can produce a most likely forecast that the central line plus or minus 1.5 sigma, in this case 90.13 plus or minus 1.5, 1 sigma is about 6.9 million in this process, and that gives us a range of forecast that is somewhat more is the most likely forecast is between, say, 80 to 100 million dollars. Another application of control charts is to establish data homogeneity or comparison of two groups. Here group A and group B are compared. If we make assumptions that these two groups are comparable, or we perhaps making an assumption that they are coming from the same system of causes. Here is the control chart for group A, and here is a control chart for group B. In both cases, separately, group A is in a statistical control, group B is in a statistical control. Group A manifests random variation and group B manifests random variation. If we're assuming that these two groups are coming from the same system of causes, in other words, they're comparable, that means that this group must fall within the upper and lower control limits of this range, and this group must fall within upper and lower control limits of this range. So we make that comparison. Here is group A, upper and lower control limits. If we extend the limits for group A, then if we're assuming group B comes from the same system of causes as group A, then all these values must fall within upper and lower control limits. However, we see that the special causes are present. Therefore, we conclude that these two groups are not homogeneous and they don't come from the same system of causes. Similarly, if I extend the control limits for group B, as I have here, extend it this way, then if we're making the same assumption, if group A is the same as group B, then group A has to behave randomly between upper and lower control limits for group B. And as you can see, we extend the control limits yet, and again we have special causes. Then we can conclude that these two groups are not homogeneous. They are not from the same system of causes.